Why don't we go ahead and get started? So welcome to the brave souls that are here in person. I guess the heat is driving people away or something like that. So just a reminder that obviously next Monday is the Phase 2 project report is due. And then you guys will actually be starting to give the presentations on Tuesday. So I actually budgeted both Tuesday and Thursday for sort of your guys' presentations. I'm hoping we'll actually be able to finish things before then so that we can sort of dive back into the material and make sure you guys have everything you need to complete stuff for the next phases of the project. But just logistically as a reminder, everyone needs to bring either on a USB or by email or something like that their presentation files that they will be using to me by basically the beginning of lecture next Tuesday. And that's just to make sure that everyone has sort of the same amount of time to work on those presentations. And then also actually just given I guess the current heat and all that, attendance on Tuesday and Thursday will be mandatory so that everyone, I'll just randomly choose on who's going to be presenting or something like that. And also just so that everyone sees what's going on, you have an opportunity to both, get feedback from others in the class and, of course, to give the feedback as well. So any questions on stuff before we dive back in? Or I guess the brave souls that are here are all set, so. Okay, so if there's no questions, then let's go ahead and sort of dive back into the material. So what we were talking about last time was basically getting into more detail about sort of timing noise, or really more specifically jitter. And where we basically ended up was talking about, in the context of, I said, well, let's look at all of the different components in the loop and see sort of how their jitter basically propagates through the PLL. So we started kind of with, let's say, the simplest things. We talked a bit about what the reference jitter does, and that's sort of fairly obvious. That just goes through the transfer function of the PLL. We then said, okay, well, how about the PFD? And the PFD, we sort of used that just as an example to sort of say a little bit about, well, why is it that even just adding some little digital gate would also actually add jitter onto your timing signal? And so, of course, the reason there was that, each of these little inverters in here has some thermal noise associated with it, or even some flicker noise, or even supply noise, or whatever it is. And so that basically variation in the voltage, or in fact, as we'll see in a second, variations even in the current, would cause basically uncertainty in the timing edges that you'd see as well. So what we basically ended up on last time was just kind of for the purpose of giving you an example of how you go about doing some of these calculations in terms of jitter, or really more importantly, translating thermal noise into timing jitter. What we started doing was basically showing how, even for the simple example of an inverter, you could basically figure out how the thermal noise of that inverter was going to be translating into timing error. Okay? So we said there was really sort of two important components there. So basically, first of all, just, if I put, let's say, a step into this inverter so that obviously I'd start pulling down that output, basically, we can kind of say that there's some on current from that NMOS transistor that's pulling down. Let's assume it stays in saturation the whole time. But of course, anytime I've got that current, I would also have some noise current associated with it. And that noise current will, of course, translate into timing uncertainty at the output. Turns out there's actually one more important component in terms of thermal noise that, or rather just noise in general, that would also cause jitter. And this is the one we actually did a more detailed derivation on, which is, even though I started nominally at VDD, there's always some basically just thermal noise from the transistor, in this case the PMOS transistor, that's holding that output at VDD, that's going to cause wiggles in the output, right? So if you sort of think about it, right when this input makes a step, I'm going to be sort of sampling that wiggle, right? So if I've sampled that wiggle, then even if I don't have any noise while I'm pulling down, just because of the fact that I started from some slightly unknown position, that's also going to translate into an error in terms of when I actually make the edge crossing at the output. Okay? So we kind of quickly went through how you would derive something like that, and it's fortunately at least, and by the way, for this part, we're really just focusing on the jitter due to that timing uncertainty, or rather the initial voltage uncertainty. We'll do in 1 second how you'd figure out the impact of the noise current. Okay? But basically, if you wanted to figure out what that is, then it's fairly straightforward. You basically just say, okay, if I want to know what the basically timing error is, then that's just going to be equal to whatever the voltage error was, basically normalized by the edge rate of my transition, right? And what I mean by edge rate here is basically just saying, okay, if I have a certain voltage error, then I should normalize it by my overall power supply, because that's sort of the total voltage swing that I need to do, and then multiply it by how much time does it take me to go from VDD to ground in the first place, okay? So we went through just a little bit of math to kind of put this into a slightly different form. But at the end of the day, it basically did indeed say that if we looked at the variance of our timing jitter, it was, of course, as you might expect, just related to KT, times whatever your sort of edge rate was, divided by something that looks kind of like a power consumption. It's not exactly really power, because in principle, you should never have the ion of the NMOS transistor flowing through VDD, right? But dimensionally, that's kind of how it looks, and obviously, the higher the VDD is, or the more ion your transistor has, that implies that you're driving more capacitance. Basically, that sort of says that increasing the power consumption is something that you'd have to do if you want to knock down this sigma squared of the jitter. Okay? Now, there's one sort of important thing to note here, which is that the variance of the jitter is proportional to the edge rate. It's not proportional to the edge rate squared. Okay? So in other words, if you make the edge rate twice as long, then that means that the variance would only go up by 2. In other words, the sigma would go up by square root of 2. Okay, so it's not exactly a one-to-one relationship. It has to do with sort of the way things get averaged out. You'll see that maybe in a little bit more detail in 1 second. But just keep that in mind, because it's sort of this minor, well, perhaps not so minor distinction that sometimes can cause a little bit of confusion. Okay? Does this make sense to people, or? Okay, so as I said, we spent a lot of time sort of deriving what happened due to that initial uncertainty. But as you can imagine, even if I had a perfect initial condition, then I'm still going to get some jitter just due to the fact that this noise current here is going to be changing the exact time at which we cross the threshold. Okay? So let's actually go through now and figure out what the impact of that noise would be in terms of causing jitter at the output. Okay, so to do that, I'm again just going to quickly redraw sort of what our model looks like, just to make sure that everyone's on the same page. Okay, so we've got some ion, we've got some noise currents, we've got some capacitance, and this time around, let's just assume that that capacitance is initially charged to VDD. Okay, so in other words, we're sort of doing like a superposition kind of thing where we're assuming that we already included the effect of the KT over C noise, so now we're just interested in the noise due to this noise current, or the jitter due to that noise current. Okay? So what do you think is sort of like the, let's say, easiest way to figure out how much jitter this noise current is going to cause? And I'll give you a hint. It has a lot to do with signal-to-noise ratio. What do you guys think? And if you're not sure, by the way, we can even just do procedurally what would you have to do. What sets the delay in the first place? What's like the nominal waveform you should get at the output over here? So if I looked at, this is of course V out. If I looked at V out versus time, what should that waveform be doing once the current turns on?
Ramp down.
Say that again?
Ramp down.
Yeah, it should be ramping down, right? Okay, so what sets that ramp rate?
Ion.
All right.
Yeah, it's set by ion, right? And it's set by C, right? So in other words, if I'm interested in basically how much time it would take me, it's something like delta V times C over ion, right? That would be sort of in time, how long it takes me to get from a certain point to another point where that distance is just in a delta V, right? So if I asked how long it takes me to do this delta V, then of course it's just set by that. Okay, let's say this is delta T, right there. Okay? So now let's assume that I didn't have any ion at all. What would the noise current be doing? But I still have noise current. What would the noise current be doing? What would that sort of look like? Yeah.
Putting noise on the output voltage.
Yeah, it's going to be putting noise on the output voltage, but what's sort of like the, let's say, what does the spectrum of that noise look like?
Why?
Ah, is it white? Because I've got a white noise current, but I'm dumping that noise current into a capacitor, right? So what I'm actually looking at is the voltage now. So what is that sort of doing?
1 over F.
Say that again?
1 over F.
Okay, you said 1 over F. It's actually 1 over F squared. Well, although even that's not entirely true, because I'm basically integrating that noise current. No, let me change the color. Right, what I'm basically doing is integrating this noise current over a window of time, right? Now, by the way, do I care about that noise current over all time? Or do I only care about it over a certain window of time?
Over the delay?
Half the fault.
Yeah, I only care about it only during the delay, right? Because once I get past VDD over 2, I basically don't really care what that noise current is doing anymore. Okay? But, so the way I'm going at this is a little bit more of the mechanistic way, and we'll see sort of how this plays out all in 1 second. So kind of what we're starting to get at now is that if I want to figure out the impact of that noise current, which as we've been saying is basically going to add some, fluctuations on top of there. What we've kind of been getting at just now is that it looks like we have to do this sort of windowed integration of the noise current, right? In other words, we have to do this sort of integration from some 0 time to basically the nominal delay time and figure out kind of what's the expected variance in the voltage due to that, right? So we can indeed do that. I'll show you maybe a little bit how you can do it in 1 second, but it turns out there's a little bit easier way to think about it, okay? So what we're basically saying is that my delta t is not just delta v times c over ion, but it's actually delta v times c over ion plus this noise current, right? So is there some, let's say, something that looks kind of like signal-to-noise ratio that you could use to figure out how much impact that noise current is really having? What do you guys think? So let's say I told you that I did that whole integral and I did the windowed thing and I figured out there's some average noise current that's affecting you during that window. How would you figure out how much jitter that causes?
Integrate it.
Okay, that's right. You integrate it, but I've already told you that once I did the integral, let's just put some numbers in. Let's say that I told you that ion is 1 milliamp, okay, and that your nominal delay is, let's say, I don't know, 20 picoseconds, okay? And let's say that I told you that after you did all the integrations and everything like that, the noise current in some, root mean sense was equal to, I don't know, let's say 10 microamps, okay? So if the noise current was 10 microamps, and the delay with an ion of 1 milliamp was 20 picoseconds, what's the jitter due to that noise current?
I'm saying like square root of dd.
Okay, we'll get to that in 1 second. I've already sort of taken into account all the square roots and things like that. Just assume magically I told you there's this annoying offset current that just had a value of 10 microamps. What would be the change in timing due to that 10 microamp change in current?
10 by 100 square, 10 micro by 1 milliamp square.
Okay, so you're right, except that I'm just asking a slightly different question. But basically, you just normalize it, right? You basically say, okay, that 10 microamps relative to the 1 milliamp, right? That would be sort of my signal, or rather my noise-to-signal ratio. And if I know what that noise-to-signal ratio is, I just multiply that by whatever the nominal delay was in the first place, right? Now, again, I didn't do it in variances here because I already did all of that. That's how I came to the 10 microamps in the first place. But the point here is that basically whatever that variance of the noise current is, if you normalized it to the on current in the first place, that's sort of like telling you the signal-to-noise ratio, right? And once you know the signal-to-noise ratio, you can use that to then figure out what is the actual timing jitter, right? Because the signal in time is kind of like your nominal delay, right? So to kind of write that out, let's say a little bit more formally, what I'm basically saying is that if I looked at the sigma of the timing jitter, but I normalized it to my delay in the first place, what I'm basically saying is that that should be equal to the sigma of my current noise divided by my on current. Okay? Does that kind of make sense to people, or? Okay, so now if I just place this into variances, because when we work with noise, it's easier to work with variances. And that basically says that the variance of the timing jitter is just equal to the variance of the noise current divided by the on current squared times the nominal delay squared. Right? Because again, I'm just working with variances now. Okay? All right, well, so now it turns out we can actually solve this fairly easily. Okay, so what is the variance of the noise current? What is that set by? In general, for a saturated transistor, what's that set by?
4kT gamma GM.
Say that again?
GM?
Yeah, you said it, just repeat it.
Well, 4kT gamma GM.
There we go. It's 4 kT gamma GM, but there's just one more kind of important thing you have to add there. The delta F.
Oh.
right? There's an alpha factor too, but let's even ignore that. There's a delta f here. Okay? Well, okay, so let's tackle the easy one first. What is GM in terms of things that I kind of know about? Or let's say digital parameters. And let's make our life easy. Let's assume it's a long channel transistor. We can come back and fix that later if we'd like.
2IT of
There we go. It's 2 ion divided by VDD minus VT, right? Okay, great. So indeed, and again, this is long channel, but fine, don't worry about it. Let's just pretend that that's indeed what it is. Okay? Okay, well, now the only magic question, or the only tricky question, is what is that delta F? Okay? So it turns out there is actually a very straightforward answer for that. The way you figure that out is you say that, okay, again, what I'm actually doing is integrating this noise current over the nominal delay time, right? If you sort of think about it in the frequency domain, or rather in the time domain, that means that you're sort of using a box integration, right? In the frequency domain, that just becomes a sinc filter, okay? So it turns out when you do that integration, which you just integrate from 0 to TP, that sinc function, the delta F you will get will simply be 1 over 2 TP, okay? Nice, simple result. Okay? This kind of make sense to people, or? Okay, so now if we actually do that, then it's just a matter of plugging stuff in, and it turns out to be pretty easy. Right? So now all we basically have is that the sigma, or rather the variance of the jitter. So now we know what the actual variance of the current noise is, right? That's just going to be 4 kT gamma times 2 ion over VDD minus VTH, right? Times 1 over 2 TP, okay? Then I just have to multiply that by 1 over ion squared times, and actually let me just call that, TD, because that's the way I was calling it before, times TD squared. Okay, so if I just clear a couple of things out here, nothing, just simple algebra, then what you end up with is 4 kT gamma ion, 4 kT gamma times 1 over ion times VDD minus VTH times TD. Okay? So notice this actually has a very similar form to what we saw a second ago, right? We have something that looks like KT divided by something that has units of power, right? Now again, it's not that VDD minus VTH is really a power supply that's being multiplied by ion, but it kind of tells you that, again, if you wanted to reduce things, you either need to increase the VDD minus VTH or increase the ion, both of which sort of imply that you're going to be burning more power, because obviously to make the ion larger, you need a larger transistor, right? You need more capacitance, and so on and so forth. Okay? And again, notice that this thing actually, the variance increases with the nominal value, and not with the nominal value squared. Okay, so in other words, making things longer, making the delays longer certainly makes the jitter worse, but relatively speaking, it's actually getting better. Okay? Does this make sense to everybody, or? Yeah.
Just really quickly repeat how you got the 1 over 2 TD for the frequency.
Yeah, so this 1 over 2 TD simply comes from doing the integral from 0 to infinity of the sine of the sinc function, where the cutoff of that sinc is set by the nominal delay. Does that make sense? Or? Okay, so and I'll just do it over here somewhere where I've got some space. Okay, so if in time my impulse response is something like this, or that's just some nominal box or some nominal delay, then in the frequency domain, if I look at the magnitude of that transfer function versus frequency, what you get is something that looks like this. Okay, now this first null here is just sitting at 1 over, and I should be more precise, 2 pi over TP, okay, in radians per second. Okay, so the way I got this, where is it? Oh, sorry, one more. The way I got this is just by integrating this magnitude squared, df, from 0 to infinity. Like this transfer function. that make sense? Or
So you're just saying that the factor of contributed by that delta after integration is 1/2t.
yeah, so basically what I'm saying is that, kind of well, okay, so intuitively it's sort of, you should already see why the bandwidth is kind of proportional to 1/TP, right? Because I'm kind of doing this windowed integration. If I did a windowed integration for a longer period of time, I would have less bandwidth, right? The only trick is, where did that factor of 1/2 come from? And that factor of 1/2 just comes from, that's basically if I add up all of the spectral components because of that sinc filter, altogether they normalize out to become a bandwidth of 1/2. Okay, that's just where that came from. So again, the math is actually not that complicated. You literally just integrate this sinc function from 0 to infinity, and indeed, this is the result you get.
So, I'm sorry, why do you start with that box function in the first place?
Okay, because remember what I'm doing is, I have this noise current, right? And for every time before the transition, I basically don't care what that noise current is, right? And basically for every time after the transition, or excuse me, after I've crossed the center point, I also don't really care what that transition is, right? So because of that, what I'm basically saying is that if I don't really care what it is afterwards, then I should just be integrating it during that delay time, right? So if I'm integrating it during that delay time, that's where I get this box filter, right? Because you can kind of think of that as being, taking a white noise current source and passing it through this box filter transfer function. Does that make sense, sir?
I had two questions. So first one is, so why don't you consider the noise on the capacitor when it's like in the constant?
Noise. Well, okay, because you're saying why don't I include the noise that I sampled previously, or?
That is from the inverter, right?
Well, okay, so this noise up here is really from the PMOS transistor, which was just quote-unquote holding the output, right? This noise right here is from the NMOS transistor when it's pulling the output down. Right, so the assumption I'm making here is that indeed the input into an inverter is a step.
Right.
It's not exactly true, but that's basically close enough for the analysis standpoint that we'll get a very reasonable answer.
Second question was, for the sinc function, you do mod square df and find the...
That's right, so I'm just doing the standard noise integral of integral h of f squared df.
Right? It's just the noise bandwidth. Sort of.
It's just the noise bandwidth, exactly. I'm just figuring out what is the effective noise bandwidth due to that box filter transfer function. Okay, any other questions on this? Or? Okay, so obviously, by the way, if you wanted to know the total jitter, you just add the variance from this and the variance from that, and you're done, right? Now, again, it's not that I necessarily use this all the time, but it's actually pretty useful, and just in terms of thinking about, well, okay, how many stages of inverters, or just how big of an inverter do I need to make sure that I don't add more than X femtoseconds or picoseconds or whatever it is of jitter into my system. Okay, and especially if you're shooting for some very, very low jitter kind of link, then you'll see that actually there's a very small number of low power inverters you could add before these jitter numbers would actually add up and sort of swamp out the entire rest of your system. Okay, so just keep that in mind because it is indeed something that's sort of important. Okay? Now that we've done sort of that long, let's say, dive into... Oh, question? Yeah.
So I imagine if your edge is already kind of messed up, then I could make my inverter as big as I want. And I'm not going to get that.
You're saying that if I feed a really sloppy edge into an inverter in the first place, then I'm just going to be limited sort of by that edge rate no matter what I do.
Yeah.
Yeah, so that is indeed true. That's not necessarily the end of the world because you can kind of think of it as, at that point, you're sort of using the inverter like an amplifier, right? So a lot like you do a low noise amplifier design, you'd be trying to design the inverter to be a low noise amplifier, right? But you are indeed correct that in general, if you want a low jitter system, that means that you want as sharp of an edge pretty much everywhere that you can, or at least as reasonably sharp of an edge as you can throughout that entire chain. That's absolutely true. Yeah.
Yeah. So if you have a cascade of inverters, so then how does this translate?
Okay. So yeah, that's actually kind of a fun one. So there's a couple of ways you can kind of think about it. Okay. So one way is I can basically apply this analysis to each individual inverter, right? And then I can just add up the variances from that whole chain, right? Which would kind of say that, let's say that each one of them was kind of uniform, they all had the same power, the same delay. And it would just tell you that the variance in jitter would go up with the number of stages, right? Or in other words, the sigma of the jitter would go up with square root of the number of stages, right? Turns out you can actually you can also just say that, okay, now I'm going to treat that whole inverter chain as kind of one big block, and then say that that whole thing is kind of like doing the windowed integration now instead of just over one inverter period, over like all of those inverter delays, right? Turns out if you do that, you'll get the exact same answer. Because what will happen is you'll just be scaling both this bandwidth and the nominal delay by the same amount, so you'd end up with the same exact answer.
But the noise is not the same. I mean, there's noise from every stage, right? I mean,
It's true, but that's why I said I'm assuming uniform stages. If the stages aren't uniform, then the first method is the right way to do it.
Okay.
Now, by the way, I mentioned that second method, because if you start thinking about something like, for example, power supply noise, right, which would actually affect all of those inverters and has a certain spectrum associated with it, and if I have a long chain of those inverters, what I'm basically doing is indeed sync filtering or box filtering the variations on the power supply. Right? I again have to make some assumptions about uniformity or the overall, let's say, supply variation to delay variation at the output, but that is actually a pretty powerful or pretty reasonable analysis technique. Stephen, did you have a question or no? Okay, great. Okay, any other questions on this? Or? Okay, so now that we've beaten sort of calculating jitter in inverters to death, so now the other question, or let's say the interesting question to kind of come back to our global goal is, well, okay, fine, so the PFD adds jitter, and that jitter actually has some certain spectrum associated with it, but how is that jitter basically filtered by the overall PLL? So first of all, just if I have jitter in my PFD, like where does that sort of come into the picture in terms of this model that I've drawn here? Like where do I have to add some jitter into the picture?
After the 1/2 pi.
Okay, yeah. So there's one of two places I could do it. I could either do it after the 1/2 pi, or since I'm still probably working in the phase domain, I'll add it in front of the 1/2 pi, right? So there's just some T jitter due to the PFD, okay? So now the hopefully very obvious question, but just to ask it just to make sure it's clear. So what would be the transfer function that PFD jitter would experience?
Low pass.
It is indeed low pass.
The open loop transfer function?
No, it's not the open loop. It's basically just the same as the reference, right? It looks exactly the same like the reference, right? You can't tell, right? So basically PFD jitter, for all intents and purposes, is just equal to reference jitter. Right? Because again, you really can't tell the difference between the two. Okay? Because it just sort of shows up in the exact same place in the loop. Right? Okay, so if we figured that out, then now we can sort of make our life more fun. We can move to the next component. So let's assume that you've built a charge pump PLL, and let's see what the impact of charge pump noise will actually be. Okay, so I'm just going to again sort of redraw my overall loop model here. And by the way, I should point out, I'm now being more careful about the factors of 2 pi because I'm going to be starting to insert noise in places where that factor actually matters. Okay, so I've got my 1/2 pi from the phase detector. I'm going to have some charge pump, right? And then, of course, I'm going to take that. I'm going to feed it into the impedance of my loop filter. Then it's going to go through the VCO, which I'm just going to model as being KVCO over S. And I'm going to turn that back into phase. So I multiply by 2 pi. That's my phase at the output. And then, of course, I'm just going to divide by n and feed back. Okay? So now, if I've got sort of noise in my charge pump, what's most likely, let's say, the physical dimensions of the noise that's going to be coming from your charge pump?
Current noise.
Yeah, you're basically going to get current noise, right? So that sort of means that we should be adding in some noise current right there, right, due to the charge pump. Okay? Okay, so if I've added in some noise current right there, now again, what is the transfer function? And by the way, the units of this are kind of funky. It's something like, radians per amp. Okay, I don't know exactly what that unit is called, but it is indeed what we end up with. So what would be the sort of transfer function we'd get from that charge pump noise current to phase noise at the output, or really to jitter at the output?
scaled version.
There we go. It's the same as the reference. It's just scaled, right? But what is it scaled by?
ICP/2
Right, so it's just scaled by essentially the gain that was in front of it. Right, so in other words, ICP over 2 pi. So when we say scaled, by the way, that means that the H of the charge pump noise is equal to the H of the reference times 2 pi over I charge pump. Okay? And again, this is just the sort of standard feedback manipulations of if there's some gain in front of you, but you know the transfer function from before that gain, then you can just normalize everything. Okay? Does this make sense to people? Or? Okay, so that's pretty easy. And again, sort of the main point there is just to say that you can't build the lowest power charge pump in the world just because if you do, it'll have enough noise current that it could actually end up dominating your overall jitter characteristics. Okay? Well, okay, so now let's see what happens if we add some noise into the loop filter. Okay, so I'm again just going to draw out sort of our model here. So again, I'm going to have the 1 over 2 pi. I'm going to add in my charge pump. And then I'm going to have my loop filter. Okay, and then that's just the VCO over here. Still, again, my 2 pi over there. And then finally the feedback. And come back over here. Okay, and so notice I add in the noise right there. Okay, because I'm basically just assuming that let's imagine that I know that there's some magic voltage noise that got added into my control voltage. Okay? Okay, so now what's the transfer function from that to phase at the output?
Bandpass.
Okay, well, you jumped a couple steps. We'll get to that in 1 second. Just in terms of, let's say, what I've written down here. What is that transfer function?
Earlier divided by the loop filter transfer function.
Yeah, so basically it's the same as we had before, right? So if I do sort of the transfer function from the loop filter voltage noise, it's just the transfer function from the reference, but now we have to normalize it by something else, right? So now we're going to be normalizing it by, again, of course, 2 pi over our I charge pump, but now we have one more additional gain block there, right? Where that gain block is the impedance of the loop filter. Okay? All right, so just as a reminder, what is the impedance of the loop filter? Typically.
R plus 1 over SC.
Yeah, it's R plus 1 over SC, which again I usually just write as 1 plus SRC over SC. Okay, just to make it clear that there's both a 0 and a pole at DC. Okay, so what is 1 over the loop filter impedance? Yes, so just say it. Okay, you guys it's too hot or something. It's SC over 1 plus SRC, right? Okay, so now, hopefully many of you guys have seen this before, but just to sort of make it clear why. So if I now just do a plot of what that is going to say about all of these different transfer functions, right? So remember, this was kind of our nominal reference transfer function, right? It was some sort of low-pass type of behavior, right? But remember, we've just now said that we're going to have to take that thing and normalize it by 1 over Z loop filter, right? So what is this shape in the frequency domain? What does that look like? Okay, almost. So, well, not quite. So is this flat and then goes down, or?
0 and goes up.
Yeah, so it's 0, right, comes up, and then it's flat, right? In other words, it's a high-pass filter, right? Because there's a 0 at 0, and then a pole, okay? So if we just draw that out, and I'll do it in a different color here, that's basically going to look something like this, okay? And by the way, notice that, the point at which it flattens out is very intimately related to what the PLL was doing as well, because it's the same RC, right? So in other words, now if I have that as the thing that I'm normalizing by, then what's the overall response going to look like due to voltage noise on that loop filter? And someone other than Shiva.
Bandpass?
Yeah, it's bandpass, right? Because I just take this thing, which is high pass, and multiply by the low pass, and of course, overall, you get something that looks bandpass. So I'll just do that in this color. Oops. All right, whole thing basically looks bandpass like this. Okay? Okay, so now, I guess keep this in mind, or hopefully, again, maybe you guys have seen this before. So now, we've just said that if I add noise onto the loop filter control voltage, then that's basically going to go through the loop and be bandpassed to the output, right? And the reason it's bandpassed, again, by the way, is just that if I've got an integration in front of it, that means that any noise at DC basically doesn't matter, right? You throw that out, okay? Well, so now I've also, unfortunately, got noise from the VCO itself, right? And as we talked about last time, if I think about noise from the VCO itself, if I have even like just some small thermal noise inside of the VCO, it actually accumulates, right? Because if I cause jitter on one edge, then I go through another inverter, I get some more jitter. I go through another inverter, I get some more jitter, and so on and so forth, right? So it turns out that typically the way you will model noise on the VCO is actually not necessarily to just directly add it as, so let's say that this was your VCO model, so you just did like a KVCO over S, right? If I had an open loop VCO, and I said that I wanted to add in, phase noise at the output, due to just, thermal noise inside of the VCO, it's kind of a little bit problematic, because technically this would go to infinity, right? It would have like this infinite spectrum. Okay, so that's kind of a pain in the ass to deal with. Okay, so usually the way you'll model the VCO noise is just instead to say that, okay, well, I know what's really happening is that I have some amount of sort of thermal noise that I'm adding inside of the VCO, and then that's getting accumulated, right? Well, so that kind of says that instead of just trying to model the phase noise directly, why don't I just model that as being some voltage noise kind of going into the VCO and then getting accumulated, okay? So typically the way people model the VCO noise is indeed to just sort of figure out what is this kind of equivalent voltage noise going into the control port of the VCO, okay? Because if you know that, then now actually life is pretty easy, right? There's no infinite quantities anywhere that you really have to deal with. You just have this spectral density of the kind of thing causing the jitter in the VCO, okay? Of course, the other nice thing about doing things this way is that now what is the response from the PLL due to this equivalent voltage noise going into the VCO?
Same as the,
Say that again?
it's the same as the loop transfer.
Yeah, it's basically the same as the loop filter, so it's bandpass filtered, right? So it's again just saying that from the standpoint of VCO noise, what we're basically going to get is some kind of bandpass filtering effect, right? Where VCO noise down at low frequency, we're just going to completely throw away, right? At some intermediate frequency near the bandwidth of the loop, it's basically going to have the maximum gain it can get. And then for some very high frequencies, you're basically sort of filtering things out, but that's really just another way of saying that you're just getting whatever the natural integration of the VCO really was in the first place. Okay? Does this kind of make sense to everybody? Or? Okay. So if that makes sense, then now we actually get into, so let's say, kind of the whole point of doing all this. Okay? Which is, if we really look at all of those different noise transfer functions, the really important point is, what does that tell us about the way we're supposed to be building the loop? Okay? And as you'll see in 1 second, there's typically basically two really important components, or at least most everything can get lumped into one of two types of noise. So either everything sort of looks kind of like the reference, right? Because you saw that for the PFD, the charge pump, all those things, they basically look like the reference, just were scaled by, fixed numbers. Or they kind of look like the VCO, right? In that they're basically bandpass filtered to get to the output. Okay? So let's just sort of think a little bit about what does that say about how we should actually build the PLL. Okay, so let's actually look at essentially the PSD of the jitter under a couple of, let's say, different scenarios, or let's say due to a couple of different sources. Okay, so for this top plot here, let's just assume that we have some white noise on the reference. Okay? And it's not really that we have white noise, but this, again, just gives you an idea of sort of how things will be shifting or changing relative to each other. So if I have white noise on the reference, and let's say I go and I do some nominal PLL design. Let's say it looks something like this. Okay? If I go and I just say, okay, well, I'm going to just reduce the loop bandwidth. Just as an example, I'll reduce it by a factor of 2 or 4 or whatever. Okay? Then I'm going to get another curve that basically looks like that. Right? Okay, so now, this should hopefully be obvious, but in these two cases, which one of those PLLs has more noise than the other due to the reference?
First one.
The first one.
Yeah, the first one has more noise, right? So the blue curve has more noise just because you're integrating that white noise over a wider bandwidth, right? So that means that if I really care about the reference noise, or things that look like reference noise, what I want to do is make the bandwidth as low as I can, right? To just filter all of that noise out, okay? Well, now let's do the same experiment with the same PLL, but this time actually let's look at the effect of what we will call VCO noise. Okay, and again I'll assume that that's somehow white, okay? So if I take my nominal PLL, let's say this one is the high bandwidth one, then as we said before, we're going to get some bandpass filter, and let me just draw it a little bit better, something that looks bandpass filtered, right? Okay, so now when I lower the loop bandwidth, in other words, when I move to that red curve, what does the new VCO transfer function look like?
Shift to the left.
Okay, is it just shifted to the left, or does something else happen too?
The amplitude reduces.
Amplitude reduces?
The bandwidth gets smaller?
I don't know. So you guys tell me what happens. So it does indeed shift to the left, but the other two things I'm not too sure about. So by the way, how was it that we were getting rid of, why is it that it's a bandpass filter? Why is it that at DC you get no noise at all, and at some intermediate frequency you get some amount of noise, and at double that frequency you get double that noise? What's kind of going on intuitively? So first of all, at DC, why is it that the noise of the VCO doesn't matter at all?
You have the pole at 0 from the loop filter.
Yeah, you've got a pole at 0 from the loop filter, right? In other words, you have an integration with infinite gain, right? So whatever noise I put into it, with infinite gain, I make that go to 0, right? Okay, so now what happens when I move to a frequency that's, let's say I add some nominal frequency, and I move to some other frequency that's twice as high as that? How much gain do I get from the loop filter, from the integration in the loop filter? I moved up in frequency. So if I just go through a 1 over s, yeah, I get half the gain, right? So if I have half the gain from my loop filter, that means that that noise makes it to the output twice as large, right? Okay, so notice that's why you get this 20 dB per decade on this side, right? So now, if I reduce the loop bandwidth to make that red curve, how is it that I reduce the loop bandwidth? What's the simplest way to reduce the loop bandwidth? Just in general, in some, let's say even in a first order feedback system, how would you reduce the loop bandwidth?
Decrease the feedback factor.
Okay, so you guys both said decrease the feedback factor. Let's even assume, because by the way, remember, the PLL, largely speaking, just looks like, it's not really exactly this, but, even if I was just doing a first order system, it mostly kind of looks like that, right? So if I had a feedback system that looks like this, how do I reduce its closed loop bandwidth?
Reduce the gain bandwidth.
Yeah, I just reduce the gain, right? I just take this A and I drop it, right? Okay, well, if I just dropped that gain, let's say by a factor of 2, okay? If I drop that gain by a factor of 2, if I had a certain amount of VCO jitter making it through there, but I dropped the gain by a factor of 2 to reduce the loop bandwidth by a factor of 2, how much jitter makes it through, relatively speaking?
Twice as much.
Twice as much, right? So I have twice as much jitter here. How about at this point here? How much more jitter do I have? Twice as much, right? So in other words, this curve doesn't just shift to the left. It actually goes up, right? So in other words, if you really draw this, it actually looks like that, okay? So it does indeed shift to the left because I did move the loop bandwidth down. So the point at which you start rolling back down does move to the left, but the whole amplitude moves up, okay? Because really all I did was by reducing the loop bandwidth, that's kind of saying that I've just reduced the open loop gain, okay? If I reduce the open loop gain, then whatever was showing up after that gain, I'm now twice as sensitive to, okay? Does this make sense to people, or? Okay, so yeah.
We also reduce the loop bandwidth, so shouldn't that move to the left? I mean, should those two be on top of each other, or should the red curve move to the left?
No, because I didn't. Because now I'm looking at it from the standpoint of the reference, right? From the standpoint of the reference, I'm really saying I've just reduced the loop bandwidth, period. Right? So again, just like there was a factor of 2 difference here, there's also the same factor of 2 difference there.
Right.
Right? So I did indeed just shift it to the left.
On the right side, why do the two curves overlap?
Oh, okay. So the reason the 2 curves overlap here is because, remember, the way we got this bandpass in the first place was that the VCO itself is integrating, right? So if the VCO itself is integrating, then simply by me changing all of the stuff in front of it, I really haven't done anything to change this. Right? I haven't changed the integration from the VCO itself, right? Or to say it really another way, by the time I get to this point, the loop gain was basically the loop gain in front of the VCO was for all intents and purposes 0 anyways. So now all that's happening here is I'm getting the natural noise from the VCO, even if I didn't have a PLL there in the first place. That's why these overlap and these don't.
Okay.
Does that make sense? Or it's a good question. Okay. Oh, yeah.
So when you say you change the loop bandwidth, can you actually change the KVCO instead of the? Because the bandwidth here, it's hard to say which bandwidth you're talking about. If you reduce the KVCO, you also reduce the loop bandwidth. But
No, but okay. So now we have to be careful because even if I reduce the KVCO, remember this voltage noise here is normalized by KVCO. So when I change that KVCO, if the phase noise at the output didn't change, then I would be scaling the voltage noise by the same way I changed the KVCO.
yeah, but okay, that's true for VCO noise, but not true for the the.
That's right. So if you're talking about loop filter noise, then it's a little bit, it's a slightly different story. That's true. Although, if I wanted like the same range and I had the same KVCO, like, if I had half of the KVCO I used to and I wanted the same range, I would have to double sort of the loop filter voltage range, and that may double the voltage there. But you're right. So maybe, to make it, if it makes it easier for you to think about, imagine that I just halved the charge pump current.
Okay.
Then I think everything would do exactly what I'm saying here.
Right.
Other questions on this, or? Yeah.
So what if the VCO has some like 1 over F cubed noise or something? Then you can't.
Well, okay, so that would say that, in this model that I'm drawing here, if it had 1 over F cubed noise, this wouldn't be white. It would have a 1 over F corner in it. Right now, that would say that basically this thing wouldn't just sort of go up like this, but at some point it would even have a higher slope on it. Right, so at some point, if I drew that real PSD, I may indeed start seeing the 1 over F cubed corner of the VCO itself. That indeed can happen. Does that make sense, or?
But wouldn't it be? It would still be at low frequency, right?
Well, it depends on where that 1 over F cubed corner is relative to your loop bandwidth, right? So if I had a super low loop bandwidth, then you would indeed see that 1 over F cubed corner due to the VCO, right? If I have a high loop bandwidth relative to that corner, then you won't really see it because you'll just be killing it by the gain of the loop. Does that make sense, or? So maybe let's just draw it really quickly. So let's say that naturally the VCO noise looked like this. And again, by the way, I'm drawing this now in like the equivalent voltage thing just so that I don't have to draw, the extra integrations. Okay? So let's say that naturally it looked like this, right? So if I take this and I pass it through a bandpass filter that looks like this, then basically, for all intents and purposes, the only thing that will do is it'll mean that my net PSD will look something like basically there'll be a floor down over here, then it'll be a floor, then essentially come up, right? Or actually, did I do that right? I know that's right. It'd be a floor, and then it would follow the bandpass filter, right? And then just look like the bandpass filter, right? So let me just line everything up.
Okay. Yeah, you're
Right?
right.
Does that make sense?
Yeah.
So you're right that it's not that it has no effect. It has some, finite effect due to the ratio of the loop bandwidth with that 1 over f corner.
All right. Yeah.
Yeah.
So what is that? That's not the origin, right?
What's not the origin?
That the PSD where you drawn it.
No, well, okay, I mean, yeah, this does technically go off to infinity, right?
Oh, no, I'm saying the x-axis. Isn't it from the oscillation frequency?
No, so this is, what I'm drawing here is the spectral density of the equivalent voltage noise going into the oscillator.
Yeah, so
Right.
that's not 0, right? Is it?
Why is this not 0?
Because isn't it like with reference to the center frequency of the VCO? I mean,
No, because again, I'm drawing the spectrum of the equivalent voltage noise going into the oscillator.
Okay.
Right, going into the control terminal of the oscillator. Right, so if I have DC noise here, that would mean, like if I have a DC shift in the voltage there, that would mean that my DC frequency has shifted.
Okay.
Right, does that make sense? Or?
Yeah.
Okay. Okay, so now, kind of, we spent actually more time on this than I expected, but that's great. You guys asked lots of questions. There's kind of this trade-off here that really should hopefully be obvious now, right? Which is that if I really had a lot of reference noise, then what I want to do is I want to push this curve as far to the left as I can, right? But notice that as you push that curve to the left, you're always going to be pushing this other curve up and to the left, right? In other words, as you try and filter the reference noise more and more, the noise you get from everything afterwards is going to increase, right? So what this is really basically getting at is that if you actually look at sort of how you should build a PLL the quote-unquote optimal way, there's always essentially an optimal loop bandwidth. Okay, that optimal loop bandwidth is basically just balancing between the noise due to the reference and the noise essentially due to the VCO. Okay, now again, when I say reference and VCO, what I really mean is things that look like the reference and things that look like the VCO. Okay? So just to make sure this is clear, and by the way, there's a few papers on this first by a woman named Majgan Manshuri, and I believe she first talked about this in ISC, if I remember correctly, it was around 2004 or so. There was also actually some work here from Berkeley by a guy named Socrates Vamvakos, where they were actually trying to build a loop that would automatically tune its parameters to try and find the minimum, like the loop bandwidth that gives you the minimum jitter. Okay? But basically, let's just see if this, you guys are sort of getting, let's say, the right idea here. So let's say that I have a ring oscillator-based PLL. Okay, so my VCO is basically a ring oscillator. And let's even say that, I've tried to make it really low power. So I've got pretty small inverters inside of that thing. So what do you think you're going to want to do to the loop bandwidth in that case?
Get big.
Yeah, you want to make it as big as you can, right? Assuming that you've got a good, clean reference, that's basically going to say you want a big loop bandwidth. Right? Okay, well, now let's say that I had my VCO. Instead, I actually used an LC oscillator. Okay, and actually not only did I use an LC, but I was really, really careful. I really optimized the hell out of the phase noise of that thing. And I did such a good job that it's better than the crystal reference that, that somebody gave you. Which, by the way, is not actually impossible, Because remember, those crystal references are like 100 megahertz, and, these LC oscillators could be at 10 or 20 gig. Okay, so that can actually happen. So in that case, what do you want to do? What do you want to do to the loop bandwidth?
Small.
Yeah, you basically want as small of a loop bandwidth as you reasonably can get, right? Okay, so now obviously you're never exactly in one of those two situations, right? There's always some balance point in the middle, right? In general, you have to look at, okay, as I move that loop bandwidth around, how much extra noise am I picking up due to the reference? versus how much am I attenuating due to the VCO, right? And as you move things around, at least in principle, you can always find a balance point where you get basically the best possible jitter performance. Okay. Now, it does turn out that actually, especially in these ring oscillator VCOs, because actually things like power supply noise and things like that actually have a really big impact, in a lot of those ring oscillator VCOs, people just try and make the loop bandwidth as high as they possibly can. But especially if you start pushing to like really high data rates, or you really start doing a very clean oscillator, then now actually the question of where to put the loop bandwidth is a much more interesting one. So you really have to look much more carefully at what are the jitter sources and where is kind of really the right spot to put that loop bandwidth. Okay?
So
Yeah.
when you mean as high as you can, do you mean with respect to settling time constraint or?
No,
stability?
because remember, there's only so high I can make it given my reference frequency.
That by
right.
then.
Exactly that, by 10 or by 5 or whatever it is. If you guys are interested, there's actually some tricks where you can mix between a DLL and a PLL and actually even get farther than that. But bottom line, you try and make it as high as you can. Yeah?
What's the limiting factor of the frequency of the reference?
Okay, so right now it's very practical. So if you want to buy a low-cost crystal, best reference you can get is about 500 megahertz or so, if you're coming straight off of the crystal, right? Now, you could indeed buy a reference that gave you something that was higher than that. So maybe it internally had a PLL. But remember, the reference guys, they want to make money, right? So they want to build something that's very highly programmable and covers lots and lots of different frequency ranges. So they usually have a ring oscillator inside of there too. So if you just went and bought a reference that was 10 gig or whatever, but it was a crappy ring oscillator reference, then you haven't really bought yourself all that much.
Well, I guess I meant more like as far as like high frequency MEMS or something, but I don't know.
Oh yeah, no, I mean, so yes, there's a whole other, let's say, discussion or a whole potential avenue of if you could get a higher frequency, let's say from a MEMS device or something you could integrate, absolutely there could be a lot of benefit from that. That's certainly true. Today that hasn't really happened yet, but in the future maybe something like that could indeed happen. And by the way, a lot of times people will actually build what's called a cleanup PLL. Well, they will really put on their own chip basically a really, really good clean LC oscillator just to get a very high frequency reference. Okay, and then they'll use that to distribute the clock or clean up their, use that as a reference into a ring oscillator based thing or something like that. Okay, great. Other questions on this? Or okay, so if there's no more questions on this, then let's actually go ahead and move forward. Okay, so the next sort of set of things that I'd like to talk a bit about in terms of timing is actually, now that we've talked a lot about how you build PLLs and sort of how you get that to give you some sort of a, reference clock in the first place, now it's actually a good time for us to come back and talk about, well, remember, usually you actually have to figure out what the clock is supposed to be in order to actually receive the data on the receiver side, right? So on the transmit side, if you have a really good clean PLL, then that's kind of the end of the story. But on the receiver, even if you have a really good clean PLL, you still have to figure out what's actually the right phase to be using to sampling the data. Okay? So just as a reminder, since it's been a little while since we talked about these things, if you remember just sort of conceptually what a CDR is doing, is basically the following. We're basically taking our incoming data. Okay, so of course, we're going to be making some sort of decisions about that data. But at the same time, what we're going to be doing with a CDR is essentially doing some sort of a phase detection. Okay? So if this is like our sampling clock, right, we're basically going to be doing some sort of a phase detection relative to that sampling clock. Okay? We're going to take those phase detector outputs, feed them through some sort of loop filter, right? Take the output of that loop filter, and then feed it into some sort of phase adjustment mechanism. Okay? And of course, that phase adjustment mechanism is going to be the thing generating the actual clock. Okay? Now, if you remember, this phase detector could actually be comprised of, another flop that's actually clocked off of a slightly shifted clock, either 180 degrees or 90 or whatever it is, depending upon, how much interleaving you're doing. But conceptually, this is indeed what you're trying to do with the CDR, right? What you're trying to do is figure out, okay, where is the right point for me to put that sampling clock in order to kind of get my data in the best possible way. Okay? So one thing that hopefully should be very obvious is this thing looks actually kind of a lot like a PLL, right? PLL also has a phase detector. It also has a loop filter. Also has some sort of mechanism to adjust the phase, right? It's just that remember, you really are working off of the data here and not a clock. Okay, so like we talked about a few weeks ago, that means that you have to be a little bit careful, or let's say a little bit clever with how you build this phase detector to actually get information about the timing of when the data is actually arriving. Okay? Okay, so let's just sort of first draw what would be, and by the way, the flow of this lecture is going to be somewhat sort of historical. So that's going to also tend to mean that the first things I show you are not necessarily the best way of doing things. But I'll hopefully also explain why it is that you wouldn't necessarily do things the way I'm initially showing them. Okay? So let's just start out with kind of like what's the simplest possible way you could build that CDR. Okay? So let's say again, I've got my data. I'm going to be feeding that to some sort of comparator. Okay? And like we said a second ago, that CDR loop kind of looks a lot like a PLL, right? So why don't I just go ahead and use a PLL to actually build that CDR loop? Okay? So basically, again, I have my phase detector. I'm going to feed that as an example, and let's say I really do this right. Let's say I have an up and a down. I feed that into some charge pump. Then I feed that through some loop filter. Then take that out. And then I feed it into a VCO, and I use that to actually generate my sampling clock. Okay? So notice here that the way I'm creating that phase adjustment that I talked about a second ago is by using a VCO, right? Now, by the way, when I use a VCO like this, I'm actually doing two things. I'm not just really adjusting the phase. I'm actually also adjusting the frequency, right? So that is actually kind of a good thing, because it means that even if I have, let's say, a slightly different reference, right? If I have one crystal on the transmitter, then by doing this CDR, then I'll automatically figure out what the new frequency should be, right? As long as, of course, I've done a good job with building the phase detector and making sure I don't have harmonic locking and all the other nasty stuff we talked about, okay? So this is indeed kind of, let's say, historically one of the first ways that people typically tended to use to build their CDRs. But turns out this actually has some pretty nasty trade-offs embedded in it, okay? So to see what those are, we have to take kind of a closer look at what's really going on with our link, okay? And in particular, what we need to do is, we said we had this discussion about what the optimal loop bandwidth should be. Well, let's sort of figure out what's really going to be setting the optimal loop bandwidth in this particular type of design, okay? So to figure that out, and actually maybe before we do that, if we really looked at this quote-unquote PLL here, all right, so again, this whole thing right here is kind of like a quote-unquote PLL. What is the reference for that PLL?
Data?
Yeah, it's the data, right? The data is your reference, okay? So that means that if we're starting to talk about figuring out what the optimum loop bandwidth is, what we need to do is figure out how much jitter is there on your reference, right? Which in this case means how much jitter is there on your data, okay? Well, so from that standpoint, the news is actually pretty bad, okay? Because if you remember, we talked a whole lot about basically, let's say that, I looked at my eye diagram that I would typically get, right? So in this one, let's even assume that I equalized it. Well, even though I might have equalized this particular eye diagram, if I only did a symbol-spaced equalizer, then on the edges, I really have no idea what's going on, right? In other words, I could still actually have a lot of residual ISI. Because of that, if you actually looked at the histogram of kind of basically what are the time crossings, in other words, what's the jitter at that sort of edge position, but you see it's actually really ugly, right? There's all kinds of junk happening over there, okay? In fact, even if you, a lot of times when you actually build the equalizer, it can turn out to be even worse than this, because as I mentioned before, a lot of times when you build your equalizer at the transmitter, the transmitted pulse looks something like this, which notice actually has multiple zero crossings in it. And if you've got multiple zero crossings in that, that tends to cause a multimodal distribution on the edge. Okay? So the real point here is that basically on your edge, you're going to have quite a bit of basically ISI-induced jitter. Okay? So, what does that say about sort of how you would like to build the CDR loop? I've got a lot of ISI-induced jitter. What should you be doing?
Reduce the loop bandwidth.
Say that again?
Reduce the loop bandwidth.
Right. Right, so what Shiva said is, what you'd really like to do is reduce the loop bandwidth. Okay, now, that's going to turn out to be exactly the right answer, but to make things, let's say, more clear as to why that's the right answer, I'm going to give you guys a little bit of a brain teaser. Okay? So, remember, this is the data in the first place, right? This is kind of the thing that I'm trying to recover. So, why is it that we didn't say that I actually want to make the loop bandwidth high? In other words, why is it that I don't want to make the thing as fast as I can possibly make it, so that if I did get some jitter over here, I would reflect that very same jitter on my data sample? Why is it that that's actually a bad solution?
Loop bandwidth can't be equal to the sort of, I mean, it's always slower than the data.
Ah, okay, so that's actually one great answer. So one great answer is, well, hey, to do what I just described, it would have to be something like, if on this cycle I saw I was off by 10 picoseconds, within half a bit period I would have to shift my sampling position also by 10 picoseconds, right? And so what Igor is basically saying is that, hey, look, come on. There's no way you can build a clock and data recovery loop that would respond that quickly. Okay? That is actually pretty much correct. Okay? That is actually basically kind of the crux of the issue. But it turns out that even just despite that, or rather I should say related to that, is the fact that, and now let's actually just draw some, let's say, simple examples. So let's say I just had, something where this was my ideal +1 level. This is my ideal -1 level. Okay? And let's say that my channel is just a very simple first-order low-pass RC. Okay? And so let's say that, I launch my bit, let's say, my 1 bit there, and I launch another bit right here. Okay? And let's assume that the sequence I'm dealing with is a long string of zeros, a 1, and then a long string of zeros again. Okay? And let's say that this is my 0 point right here. Okay? Well, so if I've got a pretty bad channel, right, then I'm going to have this sort of exponential RC settling. Right? So on that edge, it's going to look something like that. And then on the other edge, it's going to look something like this. Right? Okay, well, notice the point at which I cross 0 here and the point at which I cross 0 there, relative to sort of my bit positions, is moving all over the place. Right? In this one here, it may be crossed around the center point, but maybe even actually not quite. It could even actually be shifted to be a little bit late. But notice over here, because I didn't make it all the way up, I'm actually crossing 0 much, much earlier on. Right? So that would actually say that even if I could build the CDR that, that Igor just said is impossible to build, it actually wouldn't really help me. Right? Because even if I sampled this point late, because this was late, I had already run into the next bit. Right? And I would actually have worse timing margin than just sitting at the nominal spot that I thought I should have been at in the first place. Okay? In other words, if I just always sampled right here, that would be better than trying to find this slightly late, or trying to move the sampling point because this earlier edge was a little bit late. Okay? Does this kind of make sense to people? Or, by the way, this is actually a fairly subtle issue that I think most people, including myself, didn't necessarily understand until fairly recently. Okay? So what this really means is that indeed, because let's say the edge jitter is essentially uncorrelated with where you really want to put the data sample, that basically means that your only choice is basically to just filter that jitter out as much as you can. Okay? Now, there are indeed things that will cause just low frequency drifts, right? Like that will just shift the entire sequence around. So those you still want to be able to track. But certainly anything that's even close to a sort of cycle, or maybe 10 cycles, or even about 100 cycles or so, basically your best bet is to just not even try and catch it. is to just ignore it and stay where you used to be. Okay? So if that's the case, that really does say what you'd like to do is reduce the loop bandwidth as much as you can. Okay? Okay, so if that's the case, and now I'm just going to sort of give you another reminder. So remember, the way that we've built this CDR is we have a phase detector, we have a charge pump, we have a loop filter, and then we go into a VCO, and we use that to actually generate our sampling clocks. Okay, that's our data, of course, here. So we just said that because of the data jitter, you want a low loop bandwidth, right? But by the way, this VCO right here, a lot of times is going to be a ring oscillator. Okay? Doesn't have to be, but actually in many of the links, again, just because you want to build one link that could work over many, many different data rates, a lot of times it's actually going to be a ring oscillator. Okay? So if I've got a ring oscillator in my VCO, what do I want my loop bandwidth to be? Do I want it to be high, or do I want it to be low?
High.
Yeah, I want it to be high, right? Well, this kind of sucks, right? Because I can't do both of those things at the same time, right? I can't make my loop bandwidth low and completely throw away the jitter due to the data, and at the same time make my loop bandwidth high in order to kill all of the junk I'm getting from my VCO. Okay? So it turns out that, again, even though this was sort of historically the first thing that people really did, it's actually very, very limited in terms of the performance you can get. Because you're basically now stuck with that same sort of PLL loop bandwidth trade-off that we talked about earlier. But it's even worse because the data now actually has a lot of jitter on it. Okay? So you're sort of stuck with a bad reference and a bad VCO. Okay? So now the question, of course, to you guys, and hopefully the answer is obvious, is can you do any better than this? So is there something you can do to actually decouple these two sort of issues from each other?
Can't change the data, so you change the VCO.
Say that again?
You can't change the data, so you change the VCO. Replace
Okay,
it.
you can't change the data. You're sort of right. You said you can't change the data, so you change the VCO. You're sort of right, but there's, let's say, there's another subtlety there. Yeah.
Oh, can you just use a VCO to synthesize the frequency you want from a nice reference?
Yeah, exactly. So what you do is you use a VCO to synthesize the frequency you want, but only the frequency you want, and you use another loop just to control the phase. Okay? So what that's typically called is what's called a dual loop CDR. Okay? And it's called dual loop because really what you are indeed doing is you have one very nice clean frequency reference synthesis loop, and then you have a second loop which is just recovering the clock. Okay, it's just trying to recover the clock phase. Okay, so let's sort of draw what that typically looks like. Okay? So basically now I really am going to take some reference. This is going to be some really frequency reference, but hopefully a clean frequency reference. And with that, I'm basically just going to build pretty much a traditional PLL. Okay, so I'm going to have some PFD, some charge pump, some loop filter, some VCO. I'm going to take the output of that VCO and feed it back through some divider. Okay, so the only goal of this loop is really just to give you a nice, clean, high-frequency clock. Okay? Although actually, to be a little bit more precise, and I'll explain why in 1 second, it's actually to give you a few nice, clean, high-frequency clocks. Okay? So those multiple lines that I've drawn coming out of there are typically multiple phases. Right? So like 0 degrees, 90 degrees, 180, and so on and so forth. Okay? Because what I'm going to do with these multiple phases is I'm going to take those multiple phases and do what's called phase interpolation. Okay? So in other words, if I gave you like a 0 degree and a 90 degree clock, what I'm going to do with this phase interpolator block is be able to sort of smoothly blend between them to get you phases in between 0 and 90 degrees. Okay? We'll talk a lot more about how you actually do that a little bit later on. But basically, I'm going to be using that really now as a means to actually adjust what the phase really is. Okay? So now we can actually sort of go ahead and draw the rest of the loop. Right? So typically, the way this will look is, this is again going to be my data. This is going to be essentially the feedback signal coming back from the phase interpolator, which basically means sort of like your data and edge clocks. I put the 2 exclamation points in front of the PD there because now I'm saying this is a bang-bang phase detector. In other words, it's the 2x oversampled version that we talked about, again, several weeks ago. I'm typically going to take that, and at least in the first version of things, I'm going to accumulate it. Okay, so I'm going to take essentially either the up or the down updates from that bang-bang phase detector, just feed them into accumulator. The output of that accumulator, which of course will now have multiple bits, is then what I'm just going to be using to control this phase interpolator. Okay, so in other words, the digital bits coming out of here are just telling this phase interpolator what phase relative to these VCO phases should you actually be using, right? Or which phase should you really be generating, okay? Does this sort of make sense to people, or? Okay, so by the way, this was sort of first done and proposed by, again, actually Stefanos Sideropoulos. And it's basically, again, sort of his PhD thesis is probably the best reference to look at, okay? So there's a couple of sort of interesting things to note here. Okay? So we said we have this PLL at the top over here, right? This PLL, again, it's really just giving you a frequency reference. Okay? This thing on the bottom, if you were to, sort of call this by a name, by one of the names that we came up with for timing things, is this a PLL or a DLL?
DLL.
Yeah, it's a DLL, right? Because this phase interpolator doesn't generate a new clock. All it's doing is changing the phase, right, or changing the delay equivalently. Okay? So that's another reason why this is sort of called a dual loop, because we've got this DLL down here and then a PLL on the top. Okay? So it turns out you can actually build this DLL in lots of different ways. But there's actually another sort of kind of nice thing about the way that this thing has been built. And I'm just going to draw sort of, let's say, a dotted line to maybe highlight something. So for everything that's inside of this blue dotted line that I'm kind of drawing there, what type of circuits are those?
Digital.
Yeah, they're mostly digital, right? So that accumulator is certainly digital. Okay, the bang-bang phase detector, maybe we can argue a little bit about because, that's your comparator or whatever, but basically all of this stuff is digital, right? So that's kind of nice because it's just, you don't have to worry about extra capacitors and extra loop filters and things like that. Basically, you can build a nice, perfect digital accumulator. Okay? There's actually one other thing that's a little bit subtle about this, which is if I have a DLL like this, right? Let's just say that let's just make up an example. Okay? Let's say that, well, and actually I'll draw it in a slightly different way. So let's say that kind of the perfect position for your sampling clock to be, or for your, let's say, your data transition was there. And let's say that from whatever reason, your DLL started out with something like, minus 2 degrees away from that. Okay? So let me actually maybe just draw it in kind of the normal way. So let's say that these are just the phases. This is, let's say, versus time. And let's just say that, as an example, the ideal point for you to be is, let's say, whatever, 365 degrees. Okay? And you started out at 0 degrees. Okay? So if I started running this loop, the thing, okay, it starts coming up and up and up and up. What happens when it gets to 360 degrees?
Oscillate.
Okay. So now what Shiva said is it's going to oscillate. So the other thing that's actually kind of subtle but very clever about this is it turns out it depends a lot on how you've actually built that DLL. Okay? So if I had an analog DLL where I was just analog adjusting a delay, then if I didn't have more than 360 degrees of phase range, then I would just get stuck, right? I just couldn't do anything anymore. But notice all I'm doing here to generate the delay is just interpolating between clocks, right? I'm just interpolating between clock phases. So if I want 365 degrees of phase shift, what is that equivalent to?
1 period.
5 degrees.
It's equivalent to 5 degrees, right? So if I want 5 degrees, then all I do is I just allow this code to wrap over and choose 5 degrees instead of 360, right? So in other words, what I'm kind of getting at here is that if you've done this system right, where you actually allow yourself to just spin that phase code all the way around the circle, you can actually get infinite phase capture range. Yeah.
So why does the analog get stuck?
Okay, so it depends on how you've built the analog loop, but imagine that I just build a loop that looks like this, and I'll draw it over here. So imagine that my delay line was just a pile of inverters, right? And then the way I build that loop is I just regulate the supply of those inverters. Okay, so I've got my charge pump plus loop filter here, right? And I've got my phase detector, and then that just feeds back from here, right? So this is like your data, and that's some reference right here, okay? Well, how do you wrap this around, right? The only way you could wrap it around would be to suddenly jump this control voltage from wherever it used to be to some magic point that you now know has wrapped, right? So that's why it's actually pretty tricky to do if you really have an analog loop like this, okay? Whereas if you build the deal out of the phase interpolator, where really all you're doing is selecting which phases to blend between and how much you blend between them, well, now actually, no problem. You just wrap around and you get exactly the right phase that you wanted, okay?
Pretty easy to achieve monotonicity with this sort of phase interpolator?
Ah, okay, that's a great question. So it really depends on how you've built this. But if you do things right, and we'll actually have an entire lecture about how you do things right, then you can indeed basically get it to be monotonic. Now, if you're wondering, and this is indeed a big issue, usually where things are, let's say, most likely to be problematic is indeed when you switch between selecting a new clock phase. Right? So if I go from, let's say, 0 to 90 degrees, and then I have to switch to choose between 90 and 180 instead, that's typically where you have the biggest nonlinearity issues. Yeah?
Do you even need multiple taps? I mean, it seems like you could just build a delay locked loop in that interpolator that just, it just relies on one clock period.
Ah, okay. So you could indeed do something where, as an example, you just have a bunch of these digital delays, and then you just pick off which one of these is the right phase for you to be using. You could indeed do that. There are actually some initial implementations that did it. But remember, let's say that I'm doing, I don't know, a 5 gigabit per second link or something like that, or maybe even a 10 gigabit per second link. A typical sort of number for timing resolution that you'd like to have is on the order of 2 picoseconds or so. So, by the way, there are ways you could get 2 picoseconds from an inverter, but trust me, it's painful. And as you'll see a little bit later on, the way we build these, it's actually fairly straightforward. Or at least, it really doesn't cost you too much power to actually get that kind of resolution. Okay? That's a great question, though. All right, so we're out of time for today. So again, we'll pick back up on Tuesday with sort of your guys' lecture, so to speak. And then starting probably on Thursday, we'll dive back into the material. So I'll see you guys then.